Well, we're just about there. Welcome back, everyone. And we made it. It's now officially week 10 for the course. Welcome back, folks. What we'll be doing this week is moving through chapter 4. Chapter 4 is not going to be too long. It's going to be one other topic beyond optimization in 4.4. Then when we come back from spring break next week, we'll be moving into topics on integration after we finish off the 4.4 section. Well, not a whole lot of announcements so far. We got through exam 2, so congratulations, everyone. We'll be doing it all over again for exam 3 after the break. And other quick announcements are double check your grades. Your course grade on exam 2 is just where you were at the moment the exam was graded, but it gets updated all the time. I'll be updating this when we get on Friday, bringing in a WebAssign, grading the new upcoming quiz number 7. And if there's anything you're missing, if you're behind on any sections on WebAssign or any quizzes, you can always make up those things for full credit. Well, any questions at all, folks, before we jump back to 4.1? Okay, well, let's get started then. In 4.1, we nearly completed the entire set of notes. We went carefully because some of these definitions are pretty tricky in 4.1. We're going to apply them immediately in the section 4.2, but we'll get through one extra example first. This last example is all about the so-called closed interval method. It ties together pretty much, well, not all main ideas, but most of the main ideas that we've dealt with in these notes. The only thing we're not really going to deal with in the closed interval method is directly finding local minimums and local maximums. We'll look into how that goes in the very next section. So first, just to review, the major theorem that's going to be working for us is the extreme value theorem. It tells us that if we start with a function that's continuous and also insist that its domain is a closed interval, then there will be an absolute maximum value somewhere inside that domain, and there'll also be an absolute minimum value as well. Or said better, there will exist numbers C and D inside the domain, the closed interval from A to D, possibly the endpoints or somewhere in the middle, and maybe multiple values as well, but there will be at least one value, C, that leads to the absolute maximum, and at least one value, D, that leads to the absolute minimum, F at D. The closed interval method just tells you how to find it. The theorem guarantees their existence, and this is just a step-by-step guide on actually producing them. We'll apply it on the function down below, x minus the natural log x. It's a continuous function, and it's defined on a closed domain. So both the extreme value theorem and the closed interval method will apply. Well, it's a step-by-step guide. First thing we look for are the critical numbers. So let's review what that means right away. A critical number of a function satisfies the following. If f prime, let me fix that prime there to make it really noticeable. If f prime at the number c equals 0, then c is a critical number of f. So that's the first thing we'll do, find the critical numbers. And this definition is not complete. It's if the derivative is 0 or if the derivative does not exist. Let's make sure we include both conditions. If f prime of c equals 0 or f prime at c does not exist, then c is a critical number of f. And this is kind of a catch-all, a technicality, but it's one area we still pay attention to make sure we don't miss anything. So after we find the critical numbers, we'll find the values of f at the endpoints of the interval. It's referring to 1/2 and 2 in this example, and at any critical numbers that we find. So here we're just doing function evaluations, but notice it's talking about values of f, so the original function. When it's talking about critical numbers, we're using the derivative to find them. So already there's two functions on the table. We have to be careful with which one we're using. Then finally, step 3 says, we did function evaluations in step 2. The largest value of step 2 is the absolute maximum, and the smallest value in step 2 is the absolute minimum. So that's the whole method. We'll give it a try right away on this function down below, just to see how it goes. Any questions about the method first before we get started? Okay, let's go down the line on that step-by-step process. Step 1 really has kind of 2 steps altogether. Because we're finding critical numbers, the first step should just be find the derivative. So let's do f prime at x. And the derivative is pretty fast on this one, nothing too crazy. We've done some tough derivatives in chapter 3. But this one, we'll take the derivative of x, it's a 1, minus the derivative of natural log x. That was our last section. That gives us a 1 over x. And we're done. That's the entire derivative of that function. Now, the next part of step 1 is we set that to 0 and we solve. So now we're equation solving, and this can get sometimes pretty involved. We'll see some interesting examples in the next sections. But this one's not too bad. If we're trying to solve this equation for x, one approach could be just add 1 over x to both sides. You'd obtain the result 1 equals 1 over x. The next thing you can do is just multiply both sides by x. That'll clear the denominator. And that could have been your first step up here as well. If you added 1 over x first, then multiply both sides by x, you get the equation x equals 1. And I'll leave it as an x rather than calling it c. This is more for the definition, calling it c. But it's good to emphasize when we got the x equals 1, I'll write x equals 1 is the critical number of f. Let me fix my penmanship there. Okay, of the function f, or just f for short. So this is the one spot where the derivative goes to 0. There's no spots where the derivative fails to exist because that would happen when x is 0, but 0 is not even in the closed interval here, so we don't hit this part of the critical number definition. Nonetheless, we'll keep checking every time that comes up to make sure we never miss anything. Well, now we're on step 2. This goes pretty fast. Step 2 is going to be 3 different function evaluations. We evaluate the function at the endpoints of the domain. That'll be at 1/2 and 2. And on the critical numbers, we found just 1. So we'll do 3 function evaluations altogether in step 3. But when it says the value of f, that means we go to that function there, use the original function. So let's compute f at, let me try again, that's supposed to be a 1/2. F at 1/2, we're plugging 1/2 into that function there, giving us 1/2 minus natural log 1/2. Then we calculate f at 1. I'm going in order of the size of the critical of the numbers, so critical number is next. F at 1's not so bad. It's just going to be 1 minus natural log 1. But the natural logarithm of 1 is 0, so this is exactly 1. I don't know what the 1 above is. We'll approximate that in the calculator. The next number we check is now f at 2. F at 2 is going to be, plug it inside here, 2 minus natural log 2. And I was going to say equals, but I have no clue what that's directly equal to. We're pretty much done with step 3, but let's get 2 approximations in. So I forgot to load a calculator. Give me a moment. Okay, finally, we've got a calculator. So f at 1/2 came out as 1/2 minus natural log 1/2. So this one is at about 1.19, I'll approximate it to. Now, next one, 2 minus natural log 2. Notice these are hard to tell which one's larger, which one's smaller, unless you do more algebra or just put them into the calculator. So 2 minus natural log 2 is in fact bigger. This one is 1.31 approximated. So now we've got an exact value, exactly 1, 2 approximations on the endpoints of the domain. That just takes us to step 3. We're going to just state which one's the absolute max, which one's the absolute min, and then the process is over. Any questions on the function evaluation side in that's supposed to be step 2. Let me fix that there. Counting is harder than the calculus some days. So we went step 1, 2, now on step 3. Any questions at the moment? Okay, well, step 3, all we're doing is writing out the conclusions. And you could do it in step 2. You could just say this one is the absolute max, this one's the absolute min. But just for the sake of notes, let's write it out more carefully. I'll say the absolute max with a bit of an abbreviation, ABS for absolute. Max is equal to, here's where we would be needing to be very careful doing this as a WebAssign problem. It's tempting to say absolute max is 1.31, but we're going for dead on exact values. So similarly, on quizzes and exams, if this is on paper, you would get full credit, but then you could miss a point on WebAssign, and you just have to try again if you gave the approximation. So be sure to say in WebAssign, the absolute max is 2 minus natural log 2. It's not 2 itself. We could lose a point in either situation, quizzes, exams, or WebAssign, if we say it's 2. The maximum is the output to the function. And likewise, the absolute minimum is the smallest value, so it's not 1/2 minus natural log 1/2, because that came out smaller. The absolute minimum is 1. So that's the full write-up for the closed interval method. It's nice, it gives us absolute maximums, absolute minimums, but it's limited in its scope on how you can use it. We're going to look into problems on optimization where we don't always have a closed interval like this. So we have to extend beyond the closed interval method to show how to find minimums and maximums when the domain is, say, all real numbers, for example. But nonetheless, this is the full process. And just for the sake of visualizing what we just did, let's plot that function. F of x equals x minus natural log x. Now, this is not the function because recall it has a restricted domain, that particular closed interval. So we need to include that information. Let's write in 1/2 less than equals x, less than or equals 2. And that's the graph of our function. There's not much there. Let's see how our method worked on this. It was on a closed interval, and we said that our minimum is exactly 1. That's the second coordinate we see here. So we're seeing an absolute minimum for sure. The input is 1 and the output is exactly 1 as well, as a coincidence. We said the absolute max is 2 minus natural log 2. Wouldn't be this one because that's at 1.19. That's our upper value right there. So if we go all the way over to this other endpoint, 2.131, if we round it the same way, that's our absolute maximum. So if we're only using the graph, we have a max and a min, but if we needed to know the exact absolute maximum, now we know as well, it's 2 minus natural log 2. Well, any questions at all, folks? Getting through this process here? Okay, well, next thing we're going to take a look into in section 4.2, before we get into the optimization problems in 4.4, is what happens when you take out the closed interval. Say you're looking at a very large domain, all real numbers potentially, or maybe numbers that are non-negative from 0 to positive infinity. The methods will have to adjust, and here's where we start. If it feels like deja vu, that's kind of good in a way. We've actually been over this information when we were all the way back in section 3.2. The first thing we're going to look into is the increasing decreasing test. And this will lead directly to the so-called first derivative test. There's also a second derivative test for concavity and another second derivative test for local minimums, local maximums we'll take a look into. But before we jump into this method, let's just take a moment to kind of review a bit on how this all comes together. The derivative of a function f, again, is defined through a pretty interesting limit. This limit right here expresses the value of the slope of the tangent line, which the graph y equals f of x, at any point whatsoever, x f of x. And essentially what this derivative is telling us is, if it's the slope of the tangent line, it's telling us the direction the curve is going. If the derivative is positive, then it has to be increasing on a particular interval, it's going up. Because the derivative is the slope of the tangent line, if the derivative is negative, the tangent line slope is negative, it's slanting down, that means the function is just decreasing on that interval. The way we used this information was, really we were focusing on the derivative being a function in its own right. So we took this same information here, we didn't call it increasing, decreasing, but it was the same idea. And we were able to take a function like this and sketch the graph right down below. Let's put it on the notes just for an emphasis on what the increasing, decreasing test was really trying to say. So there's that graph once again, kind of a familiar graph when you think about it. So increasing, decreasing test tells us if we're decreasing on this interval, that means the tangent line is negative, but that just means the derivative is negative, and we can work this in both directions. Derivative being negative means it was below the x-axis, and so on. If we are increasing, that means the derivative is positive and vice versa. So that's why we said bigger than 0 here, and we drew the graph's derivative above the x-axis in this range. Then below and above, according to whether the curve was increasing or decreasing. So we can tie together where something is increasing and decreasing, but here's where it gets involved in the first derivative test. Here's the next piece of information. I'm not sure what color I'm going for. Let me go for blue. When you look at this graph here of the original function y equals f of x, notice that there's a local maximum right at that spot. The local max occurred because we went from increasing to decreasing. Or you could say the local maximum occurred because to the left of this point on the x-axis, the derivative is positive, and then it switches to negative. That's the reason we have a local maximum. Likewise, we have two other spots right here and right here. I'll just draw one arrow so this doesn't get too busy as a diagram. So this one is a local minimum value, and so is that one over there, but the diagram is busy enough. This one's a local minimum because it went from decreasing, a negative derivative, to increasing, a positive derivative. So these observations are essentially the whole idea of the first derivative test. You can see where the derivative switches from below 0, negative, to above 0, positive, you'll know you have a local minimum. If you see where it switches from above 0, positive derivative, to less than 0, negative derivative, that will lead to the local maximum, just like we saw in this diagram. Well, we're going to take a look into the entire first derivative test, the way it's stated, and how we'll use it. But any last questions or comments at all, folks, on that diagram? Okay, well, here's our first big tool that we're going to use in our optimization section, 4.4. It's somewhere. Let me bring it back up. Critical number definition is here just as a reminder. And here's finally the first derivative test. Notice it talks about a critical number right away. So it means finding the critical number is essentially the first step for almost every problem in this chapter. Once you have the critical number, you can throw it into a first derivative test, second derivative test, and so on, or the closed interval method. So if we have a critical number, that's where the derivative goes to zero, meaning there's a horizontal tangent line that we're looking into. And if the derivative changes from positive to negative, then you have a local maximum, just like in the diagram above. If the sign of the derivative, f prime, changes from negative, meaning it's going down, to positive, meaning it's turning back up, that means you have a local minimum in that case. But if it does not change sign, there's neither a local minimum nor a local maximum, and this can absolutely happen. That's what was going on in section 4.1. This example right here. On the left end, well, first we found a critical number right at zero. Then on the left end, the derivative is positive because it's increasing. Here it goes to zero, and then it's positive again. It's increasing still, meaning the derivative didn't change sign whatsoever. And that's why there is neither a local minimum nor a local maximum where the critical number occurred. So we'll come back to this example because it's a reminder, again, of why we work a little bit harder in the optimization section. We run through the whole first derivative test, because finding a critical number just isn't good enough. That's not a guarantee of a min nor a max. In fact, there could be neither a minimum or maximum. We have to go beyond the critical number and use these ideas to really prove there's a local minimum or a local maximum. But before we do those problems in optimization, we'll start with these problems. There's no context here. Here we really just focus on the calculus. Well, before we start this off, any questions at all about the method? Okay, well, part A is not asking for the local minimums or local maximums yet. We just want to find the intervals where it's increasing, intervals where it's decreasing. Recall, increasing means positive derivative, decreasing means negative derivative. So here's our step one. This all depends on where the derivative is zero in the first place, where the critical numbers are. So much like in the closed interval method, we start by differentiating the function. And again, the calculus isn't so bad. We did some of our trickiest derivatives in the last chapter. We're not going to try to put a huge derivative on here that's going to have extra steps. So this one just becomes 6x power 2 minus 18x plus 12. That's kind of refreshing in a way, right? We've worked really hard in chapter 3, and we're treated with not the world's worst derivative. Now, our goal is to set this to 0 and solve, or find where the derivative doesn't exist. But because this is a polynomial, the derivative exists at every value of x. However, at some values, it might come out as 0. So the next thing we do is we set it equal to 0. But now, because we're equation solving, what we did in the last section isn't going to help us. We don't want to add 6x squared anywhere or add 18x anywhere. Instead, we're going to use the method of factoring. Much like what we did in chapter 2, we had to factor a lot of things to make a limit come out right. So first step, let's take the greatest common factor out, 6. Leaves behind x squared minus 3x plus 2. And if you preferred, you can just divide the whole equation by 6. Different looking algebra, same result. Now in this group right here, we'll just factor this completely. So we have 6 times the group, or 6 times 2 binomials. Let's lead with x and x. Positive here with negative here means both signs are negative. And the one factorization we would probably try with a prime number like 2 is a 2 and a 1 and hope for the best. But double checking, x times negative 1 is negative x. Negative 2 times x is negative 2x, and they sum together to a negative 3x. So that's a bona fide factorization. We still don't have the critical numbers, but we can read them off. If you plug in 2 here, the equation balances. Plug a 1 here, the equation balances, 0 equals 0 once again. So that last line implies x equals, I'll go in order, 1 and 2 are the critical numbers. I'll often just say crit for critical. numbers of f. That's where the derivative goes to 0 on both of those numbers. And by the way, I was kind of lazy when I carried down f prime. I only wrote it once because I wanted to focus on the equation. But that is f prime right there. And sometimes the factored form is easier to use than the expanded form right at the top. Well, step 1 is done. And here's where we get to do some new algebra that we've never really done in class. Probably a good review from back in the day. If you're trying to find where the derivative is positive or negative, what you're really doing is solving for inequalities on a number line. So here's what step 2 looks like. There's different ways to express this, but this is a pretty good visual geometric way to tie together all the information. The domain is the entire real number line. So step 2, we're going to place, in fact, the entire domain, the whole real number line. This is defined on all real numbers going from negative infinity to positive infinity. So we're looking for both local maximums, local minimums on that entire interval. But first, we're just saying where on its domain is it increasing and where on that domain is it decreasing. It first is cut up according to the critical numbers. Sometimes in this context, these are just called cut points. We have a cut here at 1, another cut here at 2. And when we make those cuts on the number line, it gives us 3 different regions we're going to take a look into. One of them is finite from 1 to 2. The other 2 are infinitely long in length. And what we're trying to do on each of the regions is test the sign of f prime. We want to know if f prime is positive or negative here, here, and here. If it's positive here, we'll say it's increasing. If it's negative here, we'll say it's decreasing. And that's how the first derivative test is going to be involved. Well, next thing we need is a good test point, something between negative infinity and positive 1. I know 0 would do the job. It's in that range. So we compute f prime at 0. Now, again, there's 2 derivatives here. Let me put some temporary highlighting. Really 1 derivative in 2 algebraic forms. That's f prime. And for plugging in 0, that's the most convenient version. So plug 0 here and you get just a 12. I'll put here for emphasis, 12 is bigger than 0. So it's definitely positive. So we can put here greater than 0. But then the increasing decreasing test tells us if the derivative is positive, it's telling us the direction the original function is going. It's going up now. So we can say in this entire range, increasing for short. Then we just move on to the next interval. Any questions or comments so far? Okay, now there's a definite pattern that you're possibly going to notice when you're seeing these problems in the lecture notes as well as exams. You might notice that if you found increasing, the next one is possibly decreasing. And then if this one's decreasing, the next one's possibly increasing. But that's not a hard and fast rule. That depends on the original function above. We're trying to make the algebra not go too crazy, but if something's different here, if say I put power 2 on one of them or the other, it breaks up the pattern and it can go increasing, increasing, then decreasing, or vice versa, decreasing, decreasing, and then increasing. Any even exponent throws off the pattern. But if the powers on all of these groups on the outside are all odd, there's an actual alternating pattern, and that's a bona fide real pattern. But for the sake of safety and not throwing up a whole bunch of different sign rules for the behavior of polynomials, I think the best practice is just do a couple more evaluations. And if I made any mistakes and the pattern doesn't appear the way I think it should be, it could be in the critical numbers, somewhere in the calculus above, we'll spot it right away. June says, are the critical numbers just what each factor needs to plug into x to equal 0? Yeah, absolutely. So once we got this factored form, there's kind of a step in the middle that we kind of skimmed over. Let's put that step in just for emphasis to address that question. The step in the middle is that if you have 2 things multiplying resulting in a 0, then there's an immediate consequence in algebra. That means one of the factors or the other had to have been zero. It's not 6 because it's non-zero, so this means x minus 2 is 0, or this is the offending factor, x minus 1 equals 0. But then we just solve both of those equations and we get 2 and 1. And so the shorthand becomes exactly what you said. The number here that makes the 0 is the solution, but that's the step in the middle that really justifies it. Of the questions so far? Okay, thanks for asking about that. And we're going to see this kind of stuff come up actually quite a lot in this section, the next section we cover as well. Turns out a lot of the equations we solve, factoring is the big technique. And then when it's factored, that's pretty much what you're doing, setting the factors to 0, or just plugging in the right number that forces it to be 0, and you're getting your critical numbers. So now, next interval we'll pick. Notice you cannot pick a 1 for this interval. We already know that if you plug 1 inside this, or that version, you're going to get 0, either version you're looking into. You can't plug in 2. You have to be somewhere in the middle. Some people might pick a 1.1 or a 1.999. I think I would pick a 1.5. It just seems to make sense. Just make sure the number is in the middle. Calculate f prime at 1.5. Now, this is the derivative here highlighted in yellow. But when we factored it, for the next evaluations, that's the most simplified version for our purposes. So I'm going to use this version down below. At 1.5, the result is 6 times 1.5 minus 2 is a negative 0.5. Then 1.5 minus 1 is a positive 0.5. And we actually don't care about the exact value of the number. All we care about is it positive or negative? This one's negative because there's one sign multiplied, one sign negative rather, in a multiplication problem. Rules of signs say negative. So that means we come back here, f prime is negative on this entire region, and that's our abbreviated way of saying it. Just the whole function f prime is now negative. But once again, the derivative is telling you the slope of the tangent line, which is telling you the direction the function is going. If it's negative, the function's going down. For short, we'll say decreasing on that interval. DEC for decreasing. Then we do it all over again. This is just for the sake of being extra sure that the pattern holds, that's really alternating. My guess is that that's positive. We'll say increasing. But let's plug in 3 and make sure that really is what happens. F prime at 3 means plug 3 here. Again, that's just the easier version to evaluate. 6 times 3 minus 2 for a 1 times 3 minus 1 for a 2. It's all positive here, so it is greater than 0, which means the derivative is positive in this entire region. Why is that? Because it only ever hits 0 at 2. If it's positive here, it'll never hit 0 again, flipping to negative. So we just say positive in that entire region, which means the function's increasing in that entire region. Now we're ready to summarize the entire conclusion of part A. Then we'll go back to the first derivative test for the next portion. Well, any questions or comments at all, folks, getting through this part of step 2? Okay, step 3 is just summarizing what we are seeing in the sign chart. We have to give the actual intervals where it's increasing and decreasing. So watch out for this part right here. What this is asking us to do is write in interval notation. This is what WebAssign is asking as well, so we'll do the same on quizzes and exams. So to paraphrase, I'll focus on increasing first. The function f, the original degree 3 polynomial at the top of the problem, that function f is increasing on the interval from negative infinity all the way up to 1, then it switches to decreasing, but starts increasing again on interval union 2 to infinity. Notice how we wrote that. Because interval notation involves infinities with parentheses, we had to have a parenthesis here and here. But also, it's critical to have a parenthesis right at that 1. The reason being, right at 1, the derivative is 0. It's neither increasing nor decreasing. So we exclude the values where it changes directions, the turning points of the function. 2, it's neither increasing nor decreasing. It's switching from decreasing to increasing. It's at rest right at that 1 spot. So this is the interval. It's completely open on both ends. And same for decreasing. We can say, and decreasing on this interval, it's open on both ends from 1 to 2. Again, it has to be open intervals. If we put in a closed interval on WebAssign or in a quiz or an exam, we could lose some points on this part right here. Not a lot of credit. There's a lot of credit in a partially graded question just for doing all this stuff here. But that's our firm conclusion there, just with open intervals. We still haven't even used the first derivative test, but now we know a lot about the function, and we're ready to go on to the next part B. Any questions or comments at all, folks, with the conclusions we made down here? Okay, now finally, putting this all together, we want to find the local minimum and local maximum values of f. We have just the information to make that happen. Here's the first derivative test for reference. And pretty much we did all the hard work. We just have to state the values. You know, I need one other thing as well. It's the local minimum and maximum values of f, meaning the original function. So we should grab that as well for reference. Okay, I think I have everything I need. We've got the method, we've got the interval we produced, and the original function. There's lots to pay attention to at once for this part. But once we're here, here's what we can say. The local max is going to be equal to, now it's where the function goes from a positive sign in the derivative to a negative sign of the derivative at the critical number c. In other words, it's where it goes from increasing to decreasing. And sometimes people like to draw a curve where this might represent the function. That's not exactly where the function is. There's no y-axis, but it conveys what it's doing. It's going from increasing to decreasing. So there's a peak, there's a local max. The local max is f right at the critical number. Notice that's what we have down here, the critical number c as well. So we plug in f at 1. But when we plug in 1, we're plugging it into the very original function, not the derivative any longer. So this is 2 times 1 cubed minus 9 times 1 squared plus 12 times 1 minus 3. So this is 2, let's see, this is negative 9 minus 3 for negative 12, plus 12 we're at 0. Whole thing comes out as just a 2. So the answer is 2 for the local maximum. If we were putting this, say, as a problem in WebAssign, the number you're putting is just 2. If you're doing this as, say, a quiz or exam problem, just make sure you don't end at f at 1. You have to show what the value is itself, 2 here. So we had a local maximum here. But then the function, when it's in this range, it's decreasing. All the way up to 2, that's the critical number, so the derivative is 0. It had a horizontal tangent line here. Then it switches to increasing right after. That's all the first derivative test is saying. If the derivative goes from negative to positive, here it is, negative to positive, you will have a local minimum. That's just because it's going from decreasing to increasing, and you get a local minimum. There it is right at that spot. So we can now say the local minimum is going to be f at, plug in the critical number 2. This one looks like a little bit more of a computation. This is going to be 2 times 2 cubed minus 9 times 2 plus 12 times 2 minus 3. And if you're doing this as an exam problem, no harm just throwing that to the calculator. Definitely putting this on paper first is good for partial credit, just in case we make any mistakes here. But 2 times 2 cubed minus 9 times 2, which is 18, plus 24 minus 3. Let me make sure I did that right. 24 minus 3 gives us a value of 19 altogether. Oh, thank you. The number looked a little bit odd to me. Thanks for spotting that. So power 2 here, good eye on that one. That's going to change things quite a bit. That's going to be, let me just write it in as minus 9 times 2 squared. That looks a little bit more like what I was expecting, so a value of 1 altogether. Okay, so with that all done, the question is over right at that stage. We now know the local max, the local minimum. We worked it through by just doing a sign chart on what the derivative is doing, which told us where the function's increasing and decreasing. And then that's our foregone conclusion down below. Any questions at all, folks, getting through this method? Oh, geez, sorry, playing with that window there. Okay, well, the problem is over, but let's see how we did. Let's actually plot that function inside Desmos and see what it looks like. And see if these methods really are coming out the way we are expecting them to. So one last look at this problem before we go into the next concept on concavity. Let's import the function f of x equals 2x cubed minus 9x squared plus 12x minus 3. It's kind of a wavy looking function, but here it is. And if we're just looking at the graph, we can absolutely see a local maximum. There it is. The local maximum is at height 2, the second coordinate, and that matches up what we said over here as well, so that's kind of nice. The local minimum should be right at that spot. It's at height 1, just like we were saying here. So it's kind of satisfying to see how the calculus matches up exactly with the graph. So even though this is kind of a nice problem that had exactly a 2 and exactly a 1 here, this method works for a lot of different situations. It could have been the local max was something like 2 times the square root of pi, some random value. We wouldn't have saw that from the graph. We would just see the approximation. But now these methods, no matter how weird the answers get, will give us the exact value. We'll take advantage of that when we're in the next section on optimization. But let's throw this screenshot on to paper as well, just for the sake of finalizing this problem. We never needed the graph, but if we're thinking in terms of what we did in just the last section 4.1, we would have said that this value is the local max, and that this value here, we go to the y coordinate, the 1, is the local min. Well, we're going to look into these ideas of optimization a little bit more in the so-called second derivative test. But before we get there, we have another interesting concept. This section is entire title is how derivatives affect the shape of a graph. And where it's increasing and decreasing isn't the only thing derivatives are affecting. The next concept we're going to take a look into is going to be about concavity. So these definitions are quite an earful. So we're going to use the same graph we were taking a look at looking at. We're just going to recycle this thing. And think of it in terms of what's going on with the new definitions on concavity. Notice the concept of tangent lines appears in both spots of these definitions. So here are our definitions. If you have learned this before in terms of convex versus concave, and you decide to use those terminologies, that would be just fine on quizzes and exams. But for the sake of WebAssign and the lecture notes, I'll say concave up, concave down in place of those definitions. So here's how they go. It says, if the graph of a function lies above all of its tangent lines on some interval, we'll call it concave up on the interval. So concave up means the graph is above the tangent lines. And likewise, concave down means the graph is below all of its tangent lines instead. So to really visualize what's going on with concavity, we need to draw a lot of tangent lines. So let's give it a start. We'd want to start possibly where the tangent lines are horizontal because that gives us a baseline. If we drew a tangent line that goes through here, horizontal one, well, the curve is below. The curve being below the tangent line, the horizontal one, means it's concave down. So it looks like we're concave down around 1. But notice this is about an interval. We're not talking about a single point oftentimes when we define this. So if we're, say, slightly to the left of 1, say right around here, about 0.75, and we draw a tangent line, it's a little bit more challenging because it's a steep tangent line, but curve is still below it. If we draw another tangent line, say right around here, it would look about like that. Curve is still below, but this breaks down somewhere because if we're in this region and we draw a tangent line, the graph is going to be above that tangent line, meaning it's concave up around this number 2. First, here's the horizontal tangent line like before. Curve is above it, so it's concave up. If I draw another tangent line starting, say, around here, curve is still above, and say somewhere over here, if we draw a tangent line, it would look about like that. Curve is still above that tangent line, but now there's a bit of a conflict, right? There's kind of a limit to how well our eyes can detect concavity. It's tricky enough being away from the horizontal tangent line, and somewhere in the middle here, there's a transition point. Here it's concave up, concave down. I got that mixed up. It's concave down because the curve in black is below the tangent line. Here it's concave up, so somewhere in the middle it switches. And that point of switching is called the inflection point on the graph. Again, these are not easy to see visually just by visual inspection. So that's why we need to go beyond the definitions and see how calculus is going to help. We'll say a point P on the curve is an inflection point if f is continuous there, and the curve changes from concave up to concave down, or from concave down, like in our case, to concave up. In other words, an inflection point is where concavity changes. So where concavity changes. Another thing that's kind of tricky about the inflection point concept is we're being extremely literal when we say a point. This is going to be an XY coordinate, and we have to supply both the input and the output, the actual point on the graph, wherever it is. It's possibly somewhere here, but it's tough to say exactly where it is. Let me use a better color. Somewhere here is coordinates XY, which is the inflection point. So tough to detect exactly where that is visually. It's tough to find the intervals where things are concave up, concave down, but calculus can help us out. So that's what we're going to try to do next. First here, this was just us looking into the definition of concavity. There's no example to go along with it. This is going to be our picture to think about it. Any questions so far before we go to the calculus side of it? Okay. Though the way the calculus gets involved is kind of interesting in a way. Let's carry this down just to put it on paper and compare the methods all together. This next procedure is called the concavity test. Here is the increasing decreasing test just for reference. And now if we go on concavity test, this is kind of satisfying in a way. If the second derivative is positive, that automatically implies the curve. If it's positive on an interval, that automatically implies the curve is concave upward on the interval. The curve lies above all its tangent lines in that one particular interval. Likewise, if the second derivative is negative, the graph of f is concave downward. And it pairs kind of nicely in the logic of increasing decreasing test, where we said if the first derivative is positive, f is increasing. If it's negative, f is decreasing. The only issue about this concavity test, however, is we're talking about the second derivative, so we need to do a higher order derivative to work this test here. But that's exactly what we're going to try out in example 2. We're going to apply the concavity test to find the intervals where f is concave up. Guess we're using blue for that. Intervals where f is concave down. And then once we find those intervals, we'll get the inflection points on the graph. But what this should feel like very, very strongly is we're just redoing example 1. The only difference is we're going to the second derivative. We're not talking about increase, decrease. We're just talking about concavity. The methods should look very, very similar. And to emphasize that, let's carry down the step-by-step process just like on example 1. So step 1, well, we have to get to the second derivative. So here's what it's going to look like. Step 1 is really solve f double prime at x equals 0. We're still finding a critical number, but we're not finding a critical number to f. We're finding a critical number to f prime. So it's a new equation this time that we're solving on this one. So step 1, we need to take a derivative. And it's not the easiest derivative like on example 1. This time, this is a chain rule problem at the same time. So let's take our time with this one. So we'll use a chain rule to differentiate, which means there's a function on the inside, a function on the outside, and that one is the inner function. That's the derivative we'll handle second, so 2. The outer function is the natural logarithm, so that's outer, derivative 1 we take. And here's how it comes together now using the chain rule process. The derivative f prime at x. Recall we want to get to second derivative, but we have to work our way there. First, we differentiate the natural logarithm. Let's put that on paper as well. It's not a bad derivative, we just have to be expecting it. Derivative with respect to x of natural log x is just 1 over x. So when we differentiate this one, we get 1 over, in place of where we set x, we just put in an entire big placeholder. The whole input will go there. This part's the chain rule portion. We chain on a new derivative multiplied by the derivative of the inner function. So next, grab x squared plus 9. We'll go here where this x was, then chain on the derivative of x squared plus 9. It'll multiply back into the numerator, like how we did the problems in section 3.7. So f prime at x comes out as, I'll copy the denominator. X squared plus 9 goes into the bottom. Then we differentiate x squared plus 9, throw it into the top as 2x. And we're halfway to the second derivative f double prime. Next thing we need to do is differentiate it again. So next order derivative. Any questions to this step, however? Okay, so next thing we do, compute f double prime at x. But for doing the second derivative of f at x, and we're looking at this, the first derivative, the next rule is quotient rule. And you know that's good in a way. We worked hard in chapter 3. We have to constantly refresh it to keep it in our mind. So think of this as a capsule review in the middle of a problem. So quotient rule, let's do this setup structure, just like we did for chain rule. The structure for the quotient rule on this is differentiate the numerator, multiply it by the denominator copied, subtract for quotient rule, copy the numerator, differentiate the denominator multiplied, then divide by denominator squared. That takes up a lot of space when you write it out like this with placeholders, but for the sake of being careful, here's what it looks like. Then take your 2x, it goes in both these two positions here. Now take the denominator, x squared plus 9, plug it into all remaining spots. We'll go both here and here. And one last spot, don't forget the denominator, and raise it to power 2. So that's the setup of the quotient rule. All functions copied in. We'll finalize two derivatives, but then we'll go beyond, kind of like what we did in chapter 3. We're solving an equation, so we are also going to simplify it as much as feasibly possible. This one actually has a good amount of algebra, even though the function wasn't too involved to start. So here's our next step. Second derivative of f at x. This derivative right here comes out as just a 2. So we take 2 times x squared plus 9, copy all the way to here, minus 2 times x, then multiply by this derivative. This one's just a 2x. No chain rule, just a constant going to 0 here, and a power function derivative here. So times 2x on that, and the whole thing is divided by x squared plus 9 squared. And then we keep going. Let's distribute 2, combine the like bases here. We have 2x squared plus 18 minus 4x squared here, divide by x squared plus 9 squared. We never want to celebrate early on these. Again, simplify as much as feasibly possible. Just like section 3.7 with properties of logarithms, we use as many logarithm properties as possible, or else the work of the derivative is harder. And same idea here. If we don't simplify this as much as possible, well, we're just making the equation solving harder. We'll eventually have to solve something reduced down just to solve that equation. We might as well make it happen right here. So we have like terms. I'll make the order be constant first. 18 minus 2x squared. For x squared plus 9 squared. And it's still not good enough because the keen-eyed observant people among us would have noticed there's a greatest common factor, right? Simplest terms here means factored as well, because we're solving the equation set to 0, just like on example 1. So factor out of 2, f double prime at x, well, let's go with a new line, is now 2 times the group, 9 minus x squared, divided by x squared plus 9 squared. And it still isn't over because it still factors. There's a nice factorization formula here, the difference of squares, where if you have something of the form a squared minus b squared, it factors as a plus b times a minus b. Here, the a squared is really a 3 squared, and the b squared is really just the x squared. So factor that as a difference of squares, and we get 2 times 2 placeholders here, go 3 plus x, then 3 minus x. That's a guaranteed factorization, so that's kind of nice through this formula here. The denominator, we are just copying it on every line, x squared plus 9 squared. And now we are finally at that portion of step 1. We have the derivative. It's simplified as much as we can make it. So we go to that step. We set it to 0, and we solve. And this goes back to a concept that we discussed in section 4.1. Let's pull that up just for quick reference. In 4.1, somewhere down here, we're looking for critical numbers. We made a nice observation that if you're solving a fraction, much like that fraction down below, set to 0, really all it's going to amount to is setting the numerator to 0 and solving it. That's because you can always clear the denominator, and there's no harm showing that step each and every time. But here's our foregone conclusion. This implies directly that 2 times 3 times plus x times 3 minus x is zero. The denominator doesn't factor in whatsoever in setting this fraction equal to zero. It's all about the numerator. So we've set the numerator equal to zero. It's already in a factored format, which is convenient for us. And so now we can read off the solutions. One solution is -3 for x. Another solution is +3. So finally, we can say x equals -3, +3. We don't want to call them the critical numbers of f because we were solving the second derivative set to 0. So they're not critical numbers in that sense, but they are critical numbers in the sense that they're going to allow us to walk through the concavity test. We essentially did all of the hard work on it, getting to this step. But we ran out of space, so let's carry this down. So there's our original function above. Our goal is to find where the curve is concave up, where it's concave down. And even if we plotted this, it's really hard to tell. But with those two critical values right there, we're going to just let the calculus do the hard work for us. But let's plot this just to see what it looks like. F of x is the natural log of x squared plus 9. It's kind of an unusual looking function. Its domain is all real numbers because there's never a negative that shows up inside the logarithm. And it looks like it's concave down in this region, but then it switches possibly to concave up, but I could never tell you exactly where that is. However, using calculus, we're going to find exactly where the switch is from concave down here to potentially concave up on the fringes on both the left and the right. But again, we're just redoing exactly what we did on example 1. We draw a number line because the domain is all real numbers. These are going to be the cut points on the number line, and we'll test intervals. But this time we're testing them relative to the second derivative is the only difference. So let's make that be our next steps, our next stops in the process. Let's call this step 2. Again, completely mirroring what we did on example 1. Draw a number line. On that number line, we have two cuts. One at -3, one at +3. Let me fix my penmanship on that one. We're going from -infinity to +infinity. And now there's three regions to test the sign. The sign we're testing is relative to the second derivative in the concavity test. So for clarity, it helps to put f double prime on each one of these regions. And the second derivative is all over the place on the notes. It's right here. That's the second derivative, but I wouldn't want to pick, say, -4 and plug it in here. That's a lot of work. Probably going to mess it up in the calculator. Second derivative is also right here. That's a little bit easier to work with, but I'd still have to reach for the calculator. The second derivative is also right here. For our purposes of just figuring out if f double prime is positive or negative, that's the easier version to use. So here's the testing interval side of this. We'll plug in f double prime at a convenient value. It can't be -3 because that produces 0 in the second derivative. But we can go to the left, -3.5 or -4. Any number smaller than -3 will do the job. We're plugging -4 into this entire thing. So this will become 2 times. When it's right here, we're going to get a -1. Here we're plugging in the -4, so that's 3 minus -4. So that's a +7 altogether with a double negation. But notice nothing is going to happen fancy in the denominator due to that power 2, or due to that power 2 as well. It's guaranteed positive in the denominator. But just for the sake of making sure we didn't forget it, let's write it in anyways. That's going to be -4 squared plus 9 squared. Completely positive in the denominator. One negative sign says this whole thing is less than 0. That means we're negative in the second derivative on this entire interval from -3 going off to the left, not including -3. That's where it's 0. But because it's negative in that region, that just means it's concave down there. So we have concave down. We'll abbreviate that to CCD for concave down and write out fully in the notes when we give our conclusion. Then we just switch over to the next interval. Any questions so far, folks, on making that first conclusion? Okay, well, let's restart it. We go over to this one. Most convenient value would be a 0, so we compute f double prime at 0. Plugging it here, we're just going to get in the numerator 2 times 3 times 3. 0 is kind of convenient of a value. Down below, it's just 9 squared now for an 81. Whole thing is positive, so we're seeing the signs change. Same kind of pattern like exam 1. And same comment, not a guaranteed pattern, so be careful with the algebra. But because it's positive here, that tells us the curve should be concave upward. I'll abbreviate to CCU for concave up and write out fully in the notes for clarity. And then one last interval to test. On this one, we can put in a value, say 4. Let me scoot this down for the extra space we're desperately needing here. So now it's f double prime at a value, we're picking 4 as our test point in that region, which means we're plugging 4 into this entire numerator and denominator. This is 2 times 7, but a 4 here produces a -1. Then the denominator is 4 squared plus 9. I guess it's faster to say 25, but I'll leave it in that form to power 2. And again, we don't need to know the exact value. All we need to know is a sign. And due to that spot, the whole thing is negative. So less than 0. That means in this entire region, it's less than 0. But then we cite the concavity test for the second derivative. Spotting it's negative in the second derivative means concave down in that entire region to the right of 3. So concave downward there. Well, that's step 2. Really, step 2 is just a bit of graph work here, doing some test outputs, citing the test directly. And step 3, it's just a big summary to everything we've done. This was a hard one. The algebra and the calculus was a little bit more oppressive. A good amount of algebra. Really, the calculus is over on this line, and twice as many steps to get the critical numbers for the first derivative. But now step 3, we're just directly citing the concavity test. Let's begin by saying this is referring to the graph of the original function f. So we'll say the graph of f is concave down on these two regions. Concave down on -infinity up to -3 union, again, symmetrically to the right here, from 3 to infinity, and concave up on just the region in the middle. And just like on example 1 with increasing, decreasing, notice we're excluding the bounding values, -3, +3. We have to use open parentheses on both. Likewise here, it's concave up, not on a closed set, it's concave up on the open set from -3 to +3. And this is hard to spot on a graph, but now we can take another look at this. We drew a horizontal tangent line. We see that, sure, it's concave up on somewhere around 0. But what calculus told us is there's a switch from concave up around here, right at -3. And there is no way my eyes can spot that. This graph, no matter how I zoom in on it, I'm seeing concave up here. I might have assumed it's concave up everywhere, but calculus says otherwise. Concavity actually switches and turns down on the extreme to the left of -3, to the right of +3. Well, last thing we're going to do is take a look at the inflection points. All the inflection points are, all they do is, they're points on the graph of f where concavity changes. And these are just the first coordinates on the graph. To resolve what the inflection points are, we have to return back to the very original function. So notice how tricky this is. There's the original function f of x. There's the first derivative f prime of x. Then the second derivative f double prime of x. We're done with that emphasis, so we can erase that highlighting. But when we go back to the inflection points, we're returning to the original function f of x now. So that's a pretty good emphasis. That's an easy mistake to make here. Original function. Also, these are bona fide points. There's going to be an x coordinate and a y coordinate. We have to supply both. That's easier to spot in WebAssign because it just gives you a spot for both an x coordinate and a y coordinate. But be sure, let's put down a comment here, be sure to give x, y coordinates on exams and quizzes. Might as well just say that as well, and quizzes. So it's easier to forget that on exams and quizzes, but the emphasis is always going to be here. It's always going to say points as a reminder, on the graph as a reminder as well. But here's how it goes. We just take here, it went from concave down to concave up. That means there's an inflection point right at -3, f at -3. There's a new inflection point here because it went from concave up, switched concavity to down. So next inflection point at 3, f at 3. And you know, if this was a real quiz or exam problem, I'd probably be okay if you stopped right here. But WebAssign is going to throw a fit. They're going to want us to actually compute these things, the output values. So let's go a little bit step further, just for the sake of helping out with the homework. So we take -3. We're plugging -3 here, so that means it's the natural log of -3 squared plus 9. Similarly, we're taking +3 on the second inflection point, plugging into the function where the red dot is. That's +3 squared plus 9. Then it goes one more step further. Let's simplify on the inside. That's -3, comma. That's just a 9 plus 9, so natural log 18. And same on this point below. +3, natural log 18. So on WebAssign, we have to format the answer like this, and we have to give the exact value. We can't approximate natural log 18. It wants it in that exact form. That's probably a good emphasis to help out with the homework. WebAssign. Give the exact value. Well, we did it, folks. This concavity problem is a little bit longer, only because the calculus and the algebra was a little bit more involved. But once we got to step 2, step 3, and even the follow-up question, very similar to what we did in exam 1, except exam 1 was local minimums, local maximums. For concavity, we were just providing the inflection points. There's more to the story with concavity. We look at this graph one more time. It's concave down in this whole region, much like we said right here, from -3 to +3, it's concave down. And another thing that's going to be interesting is there's looks like a critical number there, horizontal tangent line. We put all that information together. What this leads on to is the second derivative test. But this one is a little bit tricky. When you read this, if you're like me, it probably hurts your brain a little bit. It almost looks like there's a typo here. The second derivative positive leads to a local minimum, not a maximum, and the second derivative negative leads to a local maximum, not a minimum. And that's really pretty weird. We're going to spend some time discussing why this is in relation to graphs like these above. Notice that this is concave up, but that's a local minimum. There's a opposing direction of concavity versus the conclusion of minimum and maximum. So we'll take some care and thought in looking into this when we come back on Thursday. Well, any last questions at all, folks, on the conclusion with the concavity problem? Okay, well, have a great night, folks. When we come back Thursday, we'll be back to it. Thank you.